Hi, welcome everybody as we're getting our attendees loaded into the room. We'll be with you in just a minute to begin our feature presentation. Hi everyone, and welcome to today's live webinar series on hydrogen auxiliaries. Today's topic is best practices for hydrogen safety with a focus on dual hydrogen control panels, or DHCPs. I'm Rachel Seiler, today's host and marketing communications manager for E1. Before we get started, I do have some housekeeping notes. All attendee lines have been muted. We'll be recording today's session, and an archived edition will be available on E1's website and on our YouTube channel. Upon successful completion of today's webinar, you'll receive a PDF of this presentation, a video that a presenter will reference, as well as a certificate of attendance. And of course, we'd love to hear from you. We've allotted at least 15 minutes of Q&A at the end of today's session. So let's make good use of this time. And if we don't get to all your questions, we'll answer them in a follow-up email. So now, without further delay, I'd like to introduce today's presenter, Gus Graham, who is E1's Director of Products and Markets for Hydrogen Systems and International. Gus has more than 25 years of experience in the power industry. He holds 3 patents on controls optimization of reformer-based hydrogen fuel cell systems, and has authored several technical papers and presentations for E1. Colleague, take it away.
Thank you very much, Rachel, and good afternoon, everyone. Hydrogen's use as a cooling gas for large turbo generators in the power industry dates back to the 1930s. Hydrogen's unique characteristics demand constant vigilance by plant owners, operators, and maintenance personnel to ensure safe plant operation. The continued impact of COVID-19 on 2020's outage maintenance plans, coupled with recent catastrophic industry events, have reinforced the critical importance of robust training and maintenance programs. As Rachel alluded to, today's discussion will focus on your hydrogen auxiliary system, best practices for hydrogen safety, with a particular focus on E1's dual hydrogen control panel. The acronym we use is DHCP when referring to this piece of equipment. During today's webinar, we'll review hydrogen and the properties of hydrogen gas. We'll discuss the hazards when working with hydrogen. We'll discuss what a hazardous area is and what the best practices are for working in a hazardous area. Then we'll review what your DHCP is and how it works, and review the maintenance programs associated with your DHCP. So back in the 1930s, when the demand for power increased and the size of the generators were growing, generator manufacturers were looking for the most efficient manner to cool their cooler generators, and they turned to hydrogen gas to enable them to reduce the size of the overall footprint of the generator. Hydrogen has unique characteristics of being the lightest element with the lowest density and having the highest thermal conductivity. This combination makes it an almost perfect gas from a mechanical engineering standpoint in heat transfer and thermodynamics. But when working with hydrogen gas, we have to be very cautious of the main characteristic of its explosive limits. Hydrogen has the widest explosive limit of any gas, a concentration of 4% to 76% by volume in air can maintain a flame or explosion. Hydrogen also burns with an almost invisible flame. So in the power plant, if you have a hydrogen carrying pipe that has a leak and somehow has ignited, that flame will be very difficult to notice unless it's an extremely dark area of the plant. So tools such as infrared cameras and thermal imaging scanners will be necessary for locating that. Hydrogen is also produced locally within the power stations through the process of electrolysis. That electrolysis is from water, and hydrogen is the most abundant element on Earth. As we noted, there is hazards with working with hydrogen, specifically around its explosive limits. On the screen here, we have two examples of catastrophic failures associated when working with hydrogen gas. In the upper left-hand corner is an example of a hydrogen-cooled generator that catastrophically failed during the purge procedure of the generator. So this was a process failure whereby not fully understanding the condition of the generator resulted in the explosion and damage shown on the screen. In the lower right-hand corner is an example of the storage, a failure that occurred during refueling of the bulk hydrogen storage container. In this case, there was an equipment failure. The rupture disk on the bulk storage container had been recently maintained, and there was a faulty element that resulted in hydrogen pooling in an area of the plant that was not designed for hazardous area. There was a resulting ignition and the extreme damage, as you see in the photo there. Unfortunately, in these two events, there was a loss in life associated with one of the incidents. So I mentioned hazardous areas on the prior slide. Hazardous areas are simply places where concentrations of flammable gases, vapors, or dusts can occur. These hazardous areas are classified based on the risk of an ignitable concentration forming in that area. And you may also hear the term classified area when referring to a hazardous area. It is the responsibility of the power plant to define these hazardous areas within the plant, and that typically occurs during the design and construction phase. You'll hear terms like zone or div, and those refer to the classification area. So under the current standards, the normative is referred to as the zone 0, a zone 1, or a zone 2 area. And when we're talking about work around the power plant, a predominant amount of the areas are classified as a zone 2 area within the power plant. So each piece of equipment that is carrying the hazardous gas, in this case we're referring to hydrogen, these pieces of equipment can create a hazardous area in a zone around the piece of equipment. And that area is predicated based on the risk of a leak forming in the network of piping and connections on the piece of equipment. And the manufacturer of the piece of equipment follows the code and standard to define a bubble around the piece of equipment associated with those risks. And then you'll have a map of that piece of equipment as shown on the screen here with the shaded area. And that would denote that within that shaded area, that would be considered a zone 2 area around the piece of equipment. So within the power plant, with multiple pieces of equipment that are carrying hydrogen gas in a given area, then you have this large area of the plant that becomes a concern for area classification. And it's a best practice when we're talking about these hazardous areas to restrict access and clearly mark the hazardous areas within the plant. So on the screen in front of you is a photo example of a plant, and this one happens to be in Indonesia, where inside of that caged area has a locking door to restrict access. All of the pieces of equipment that are associated with hydrogen, so your seal oil skid, the hydrogen gas dryer, the gas manifold, the hydrogen purity cabinet, and associated monitoring equipment, is all located within this enclosed area with limited access. And as you can see on the screen, very clearly noted with the risks and the safety precautions that are required to be working in that area. This would be an extreme case. In many plants, there's markings on the floor with signs hanging up. But the caged area, internationally particularly, I find is a more common way to really ensure the safety of the area, but restricting the access to a certain group of folks that are trained to work there. One of the principles that E1 has been promoting for several years, we refer to as the hydrogen safety triangle. Now, we're all familiar with the fire triangle, and that's represented on the middle of the screen there with the red triangle, whereby one leg is the air, the other leg is the fuel. Those two legs in the right combination, in this case for hydrogen, it's that 4 to 76% by volume in air. And in the presence of an ignition source, which represents the third leg, would represent when a fire or explosion could occur. The orange triangle surrounding that, comprised of the right equipment, the right processes, in conjunction with well-trained people, represents a safety triangle within your plant. And that's something E1 we continue to promote, to focus on having the right equipment, the right processes, and the right well-trained staff working in the hazardous area to ensure safe plant operation. So when we talk about work in our hazardous areas, obviously these require precaution. And operator training is the most critical element of safe plant operation. We've already reviewed adequate signage, identifying the hazardous area within the plant, and prescribing what safety precautions and equipment need to be followed when working in that area. One of the more prominent and growing elements we see in the industry, particularly in Europe, is the use of qualified EX certified maintenance personnel when working on equipment in the hazardous areas. Testing houses such as Intertech, UL, FM, they offer training courses that you would send your technicians or maintenance personnel or engineering staff to. It's called CompX training. And when working in Europe, it's becoming more and more prevalent that that is a requirement to have only CompX certified personnel when working on the equipment in the hazardous areas. Specifically for hydrogen, in our hazardous area associated with hydrogen, calibration of your hydrogen purity meter is absolutely critical. You always want to be able to trust your purity measurement and know that it's in a safe zone. And again, in this case, it's above that 76% explosive limit, well above, and above 90 to 95% is what we're looking for. Strict adherence to the generator purge procedure. We reviewed the catastrophic incident a few slides ago that occurred during the purge process. This is the most critical time when you have the opportunity to mix air and hydrogen in the generator if the procedure is not followed properly. We want to eliminate that as much as possible during the purge process. That's why that procedure is so important, and ensuring that that procedure has been updated and maintained based on any changes that you've had in the plant for equipment that touches hydrogen or touches the generator. So constant review of that procedure, extremely vital. Use of only spark-free tools in the hazardous area. Aluminum bronze or copper beryllium alloys are available, and those tools do not cause a spark when they strike a steel pipe. Very critical to eliminate that third leg of the fire triangle, that ignition source. And adhering to the OEM prescribed maintenance on all the equipment operating in the hazardous area is very vital for safe plant operation. So in the face of all that, our power industry is under stress like many other sectors. Our generator fleet is getting older, and our associated hydrogen auxiliary equipment is getting older. Our workforce is getting younger and leaner, and the training programs available to our new staff are less frequent. Utilities are asking generators to run longer between outages in an effort to reduce maintenance costs. So we have older equipment, less trained personnel running longer between maintenance cycles. These are a plant operator and utility. It's a very stressful situation. And this year in 2020, COVID-19 has continued to affect the outage maintenance schedules. So things that were planned this year in the spring and the fall have either been eliminated or reduced because of the COVID-19 situation. So again, stretching that outage, stretching that maintenance even further. These factors combine to increase the importance of a well-managed hydrogen auxiliary maintenance program. So let's turn our attention to your DHCP. Again, DHCP stands for Dual Hydrogen Control Panel. And we'll review what it does. It has two main functions. The first is to measure and monitor the generator purity. And that's a safety feature and required on all hydrogen-cooled generators. The DHCP monitors hydrogen in 4 locations, 3 of them during normal operation. Those would be from the turbine-end seal drain enlargement tank, from the collector-end seal drain enlargement tank, and from the generator case. The DHCP can also sample gas from a purge sample port located on the manifold, and this is used when generator purge procedure is taking place to monitor the conditions of the gas as you're transitioning from hydrogen to air. The DHCP also plays a role in the efficiency of the generator by maintaining generator purity through the control of the scavenging flow rates. Hydrogen is vented from both the turbine end and collector end seal drain enlargement tanks through control valves located on the DHCP panel, and this maintains the generator purity. It's important to note that the DHCP is specifically designed for use on generators with scavenging seal oil systems, in particular, the larger GE Frame 7 and Frame 9 gensets. We mentioned the role that the DHCP plays in efficiency on the prior slide. On the screen in front of you is an example of a study that was conducted some years ago. Now, this study was conducted on a coal-fired generating plant. So the exact figures on the screen may not apply to your generator today. But what's important to note here is the impact that low purity has on the losses in the form of kilowatts of energy that are converted to heat, and through the losses associated with rotating that rotor through a denser gas, and that plays a role in cost. You're losing that fuel, instead of turned into electricity, is now lost in frictional losses within the generator. So maintaining the generator purity at the OEM prescribed levels ensures the optimum generator efficiency and maximum dollar output for your unit to the fleet. Excuse me. So specifically, how does it work? So the DHCP has 2 thermal conductivity analyzer cells that continuously monitor the turbine end and collector end seal drain enlargement tank purity levels. These analyzer cells are located in the large flame-proof enclosure located in the lower left hand of the unit shown on the screen there. The scavenging flow rates are set during commissioning, and they continuously vent 1,000 cc's a minute of hydrogen gas per side, so out of the turbine end and out of the collector end, to vent. And the total flow meter on the screen indicates that flow rate. In the event that the collector end or turbine end purity levels drop below a warning level, a solenoid will activate in the DHCP to increase the scavenging flow rate to a total of 2,000 cc's per minute of hydrogen per the affected side. Once the purity level goes above that warning level, the solenoid will close and the normal scavenging flow rate of 1,000 cc's per minute will be returned. Once per hour on units that are directly coupled to the control system will send a signal and switch the turbine end and collector end sampling to the case. And you'll sample from the case for 10 minutes per hour. And what that does, it allows the control system to compare the case purity sample to the seal drain enlargement tank purity. The case sample should run higher than both of the ends. And when you look at the end, the turbine end or collector end value, if it's drifting further away from the case, it's an indication that the seal on that end of the generator could be deteriorating and be in need of maintenance. So some other functions that the DHCP performs, it's also measuring and monitoring the generator fan differential pressure. There's a gauge and a 4 to 20 milliamp pressure transmitter. That signal is sent back to the control system as well. In the event that the purity analyzer can't be trusted or there's a concern, the differential pressure can be used to map to a purity level. It's one of the original methods of monitoring purity in these hydrogen-cooled generators. The DHCP has large desiccant-style purifier cartridges, one on the turbine end sample line, one on the case sample line, and one on the collector end sample line. This ensures to protect the analyzers from oil contamination. We're sampling from the seal drain enlargement tanks. So that's an oil source. The opportunity exists for some oil vapors to be brought in or droplets, and that could cause an issue with the reading of the analyzer and needs to be attended to, and the filters will protect the analyzer from that. In the event that you lose control from the DCS or it's not available in some of the installations, the DHCP can be manually controlled with switches that are located on the front of the flameproof enclosure. These switches control whether you're sampling from the turbine end, collector end, or the case, and can be used to increase the scavenging mode, as well as selecting calibration and purge mode. So one of the first pieces of information it's critical to have for your DHCP is the model and serial number. This information is located on the system nameplate. The system nameplate is located in the lower right-hand corner of the large flameproof enclosure in the bottom of the cabinet. The model and serial number are located here, as well as the manufacturing date and some other information specific to that DHCP. And when you call into E1 for support on your unit, providing this information will ensure that you get efficient problem resolution and that we provide accurate spare part support to you and your staff. So as far as operating your DHCP, one of the first things you need to understand is where to go for critical information. And that's located on the DHCP displays. You'll notice that the DHCP has two displays. Again, that dual term refers to the fact that we have two analyzers. Each analyzer has a dedicated set of electronics and a dedicated display. On the DHCP display is a multifunction LCD, as indicated on the lower portion of the screen here. That multifunction LCD allows you to gain access to critical information, control parameters, fault codes, settings, and the ability to control the unit through different modes of operation. Referring to your DHCP software manual to provide specific details regarding the menu navigation. In the video that you'll be sent a link to after today's webinar, we walk you through the basic modes of operation of the DHCP multifunction display. So let's talk about maintaining your DHCP. The first thing we want to do is keep an eye on it. So on your daily checklists as you walk through your plant, the first thing we want to do is we want to look at the LED status on each of those display panels. We want to confirm that the AC power LED is lit, confirm that there is no trouble LED lit, and confirm that the normal H2 and air LED is active. We want to check our purity readings. When you're sampling from the ends, GE recommends that purity level will be between 94 and 96%. If while you're monitoring the unit, it's in its case sampling mode, you'll notice that the purity should be up around 98%, as high as 99% on very tight generators. One of the things that we get when people call in is they've got a concern that their generator's not operating at 99% purity. Each generator manufacturer has a different expected purity reading. So potentially if you're coming from a plant that is operating a different manufacturer's generator that may operate at 99 or 99.5% purity, if you're operating a unit that has a DHCP, these are the values that are anticipated and expected on your unit. Continuing with your daily checklist, you want to confirm the flow settings. So at the top of the unit between the two display panels are 3 flow meters. The 2 outer flow meters represent the analyzer flow on the left and the right to the analyzers associated with them accordingly. The analyzer flow should be 500 cc's per minute. This can be adjusted by adjusting the ball valve directly right there on the flow meter. The total flow meter is the one in the center, and that should be between 3,000 and 5,000 cc's per minute. And that'll vary depending on whether or not you're in increased scavenging mode. So your base flow rate is 3,000. That's both analyzers at 500 for 1,000 and both ends at 1,000. So that's your total of 3,000. If you're both ends at increased scavenging mode, then they're both at 2,000, and that 1,000 for the total flow of the analyzers brings you up to 5,000. So the analyzer flow can be adjusted during normal operation. The increased scavenging flow and the scavenging flow rates are adjusted during an commissioning or during an outage period. The next thing you want to look at is your valve lineup, and just below the analyzers is a series of manual valves, and we want to confirm that the upper row, the ones identified in the red circles, HVs 2971, 72, 73, 74, are all rockered to the on position, and that 2978, and that's the case sample to the lower right, is also in the on position. Excuse me. And lastly, we want to look at our solenoid valve positions. And those switches on the face of the flame-proof enclosure should be all rockered to the full counterclockwise position. In addition to your daily checks, a couple things to add on your weekly checklist, and that's to check your moisture indicators. The moisture indicators are the spherical brass elements located above the purifier cartridges. When they are clean and brand new, they're a blue color. When they are white or yellow, that's an indication that there's been breakthrough in your purifier cartridge. In the event that the indicator is yellow or white, you need to change the purifier cartridge and the moisture indicator. If you're not changing them on a weekly basis, well, you shouldn't be changing them on a weekly basis, but if you don't change them on your weekly check, you should perform a blowdown. There's a valve located beneath each of the purifier cartridges with a cap on the outlet of that valve. You remove the cap and you rocker the valve to the on position, and that would release any liquid oil or moisture that's collected in the pipework. This should only be performed once checking and following safe plant protocol for the presence of hydrogen gas. So in addition to your daily and weekly, we've got a biannual checklist that should be performed. The first is through the multifunction display, checking your power log. There's several circuit boards within the DHCP that rely on different power sources. The power log records the value of those power outputs, and that is accessed through the log menu. The next thing to do is to view your calibration parameters and your cell voltage. Those are viewed through the view menu. One of the best practices would be to keep a logbook to have a history of this information, and then be able to refer back to it on the every 6-month check. And to have it available when you call into E1 if there were a problem. You can run system diagnostics. This is accessed from the test menu. The diagnostics will perform a contact test, which would cycle all the contacts on the I/O boards. A keypad test can be conducted to ensure that all the functions of the keypad are working properly. An output test can be performed, which will vary the 4 to 20 milliamp signal, and you can validate that the control room settings are active and reading those properly. The power test will check those supply voltages we mentioned that the power log is recording the values of. And the relay test will test the relay functionality of the I/O board. When conducting these tests, it's important to note that there could be an impact on your runback system. So it may be necessary to force points in the control room before you run the system diagnostics test. And then the last thing we recommend every 6 months is to perform a calibration of the analyzer cells. This procedure is accessed via the setup menu and is also referenced in your manual. And again, because at this point you're taking the cell offline to perform calibration, it may be necessary to force points to prevent an issue with a runback, because the analog signal for the purity will be varying greatly during the calibration. And again, the procedures we're referring to here will be also reviewed during the video that we'll be sending out after the end of the webinar. So I threw up a few maintenance-focused, frequently asked questions we get on the hotline. The first one is, does oil contamination damage the purity cell? And the answer is no. The oil affects the cell accuracy, but doesn't affect the longevity or performance of it, other than affecting the accuracy because of the sheen of oil that forms on the thermistor within the design. Our decontamination procedure will restore the cell back to factory performance. Do I need to change the purifier cartridges when I change the moisture indicators? And the answer is absolutely yes. The moisture indicator, again, is just an indication that you have a breakthrough of the cartridges and that they're saturated. So once you have the indication on the moisture indicator, you need to change both that moisture indicator and the associated filter. And can I change the moisture indicators and purifier cartridges while the DHCP is in operation? The answer is yes. The circuit associated with the moisture indicator and purifier cartridge can be isolated. It's important at this point to follow plant safety protocols for work in a hydrogen area. As I mentioned earlier, it may be necessary to force points as well, because you'll be isolating the flow of gas through that circuit during the period of time you're performing the maintenance procedure. So in review, we discussed hydrogen properties and the hazards when associated with working with hydrogen gas. We reviewed what a hazardous area was and the best practices for working in a hazardous area. We discussed the function of your DHCP and how it works, and we walked through the maintenance procedures associated with your DHCP. So at this time, I'll take any questions that you may have. And as always, it's all about safety, risk mitigation, and reliability. Thank you.
Gus, thank you so much for that excellent presentation. So we'll start right in on our Q&A session. We seem to have plenty of time for that, so don't be shy. So Gus, here we go. Okay, we have a couple questions from actually the same individual. What is the standard voltage we should get during calibration?
Okay, good question. And that varies based on the gas that's being calibrated. So it's probably best, I don't want to repeat incorrectly the information that's going to be provided by our great lead service technician. Chad will be reviewing that during the video, and he'll walk through what the standard ranges are expected on each of those voltages as you apply those gases. During normal operation, the sample voltage should be between 3.5 and 4.0.
Okay, and then their follow-up question is where to recondition the thermo-conductivity analyzer. Our location is in the Middle East.
So there is no reconditioning. What we can do, it depends on the situation of that particular unit. We have agents located, channel partners in the Middle East. So we can assess the situation on your particular unit. We can perform a cleaning procedure on your machine. We have a service technician that's semi-permanently stationed there and that could provide that service. From a reconditioning standpoint, if the cell has failed, we would recommend a replacement with a new cell. So it'll be dependent upon the specific condition of your unit. I think the best thing to do would be to call into our tech hotline, provide the information associated with your unit, and we can take it from there. Okay, and I think you kind of answered this as well, but the third question from this individual is there a cartridge available for the thermoconductivity cell? So the thermoconductivity cell itself is a replaceable element. That would be what we would offer as a replacement if that has truly failed or reached its end of life on your specific DHCP. Okay, thank you. And what is the full form of DHCP? Full form. I don't know if they're wondering, maybe they came in late on the... Oh, maybe, okay, so yeah. Dual, yep, there we go. Thank you. So from an acronym standpoint, DHCP stands for Dual Hydrogen Control Panel. And again, that's an acronym for GE's specific reference to it. If you have an older GE machine, they might only refer to it as a hydrogen control panel. Okay. What is this is a new question. What is the PC percentage and how would this affect the measurement? This is somebody who's been playing with their machines. So PC stands for purity compensation. That's a factor we use in the definition of that particular purity cell to ensure that we maintain full accuracy of the cell across the range of performance. So purity compensation factor is fixed at the factory when we manufacture that cell, and that is an element that is put into the software when you replace the cell with a new cell. The purity compensation factor for the new cell would have to be entered into the software so that the mapping logic for the purity value is carried over for that specific cell. I hope that answered the question. Okay.
Okay, very good. This question comes from Ken. CO2 is used to degas generator and purge out H2. Can the DHCP also monitor the degas process in terms of H2 being exchanged by CO2? And do DHCPs have temperature compensation for purity accuracy? So a couple different questions there.
Oh, very good questions. So the first question about CO2 measurement, yes, that is the fourth measurement location that the DHCP has. And it's typically located on the manifold, the gas manifold area. A sample line is run from the gas manifold to the DHCP. And then there's a manual valve and a solenoid valve that's activated to pull the sample from that location. And then you set the analyzer for the purge mode for hydrogen and CO2, and then CO2 and air for the final step. The second question was in regard to temperature compensation for accuracy. Yes. So E1's approach to that is that we have a cell block heater that's part of the thermal conductivity cell. What we do is we elevate the temperature of the gas above the ambient temperature, and that enables us to eliminate the temperature effect, the ambient temperature effect on the gas sample, to ensure an accurate response across all ambient temperatures.
Okay, and our next question for you, Gus, is how much can the purity reading accuracy be affected by oil and moisture present on the machine tubing?
So we don't have we don't have a study on the exact percentage impact. We know it does have an impact, and it'll vary based on the level of contamination. So unfortunately, we don't have a study that says, you know, if you've got you know, one micrometer of oil on the bead versus 2 micrometers of oil. We just know that it does have an impact. I think one of the larger issues we run into is the inability to properly control the scavenging flow rate because of the oil contamination. And that becomes an even larger issue when you're trying to maintain your purity and you're unable to get the right flows or know that you've got the right flows on your machine to maintain that purity. So the combination of the inaccuracy of the purity reading and then inability to control the flows where you want to become a concern.
Thank you, Gus. Good afternoon. Is there any shelf life for hydrogen stored in cylinders?
That is a question I don't have the answer to, but I would check with wherever you're purchasing your cylinders, the manufacturer of that hydrogen gas should be able to provide that answer for you.
And some more questions coming in. Please ask away. How can we link the dew point gauge readings with H2 accuracy of display?
So dew point has a very small effect on purity level. It would take a very, 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 very high dew point to even begin to approach an effect on the purity reading of the gas. I don't have the exact values in front of me. There was a study conducted to show at what dew point you even begin to affect purity. I can take that question down, Rach. We can do a little research and try to get the answer back to that gentleman or lady,
Sure.
Whoever provided the question. Yeah.
Very good. And just to revert to the previous question, the attendee provided a little bit of clarification, so this might help. So is there any shelf life for hydrogen stored in cylinders? And he means from the hydrogen generator. So does that help at all, or?
Yes, I can imagine. Yeah, so that bottled gases have a dew point of minus 70 degrees centigrade. So the only thing I can think of that would affect the gas would be a contaminant, and you're getting 4 or 5 nines worth of gas. So I don't believe that there's a shelf life concern, whether it's from bottled gas or from a local H2 generator to a bulk storage tank. But again, this is best passed along to whomever your supplier of hydrogen is, just to confirm that.
Okay, very good. What is the calibration frequency of DHCP, and how frequently is the replacement of moisture indicator and filter cartridge required?
So we recommend a biannual calibration every 6 months, and that's to maintain the stated accuracies in our catalog. We can extend that to a year. Many plants wait and do it on an annual basis. And that comes to your second question, how frequently do you replace your moisture indicators? That's going to depend on the amount of oil carryover you're getting in your sample lines, which is a condition based on the design of the seal drain enlargement tank. GE has gone through several iterations of that over the years. There's some machines that are more prevalent to having oil carryover in the sample line and in the scavenging lines, and there's other machines that have less carryover. If you have a machine that's got a large carryover, E1 does offer an additional filtration kit that can be installed between the sample point and the DHCP to help offload some of the removal of that oil contamination.
Okay, and how much is considered a normal consumption of hydrogen? In our plant, we have a consumption of 4 cylinders per day for 1 generator.
I would have to take that one offline and get back to them, and that'll we'd have to look at the flow rates and do a conversion back to cylinders, which I don't have that right in front of me today. I apologize.
Okay, but we'll certainly follow up with this attendee. And can the DHCP be located outside?
Yes, we have 2 models. Throughout the presentation, the model that I represented was a model that is typically located inside the collector cabinet. And that's because it has a better visual ability to see all the components. We have another design that's located or housed in a NEMA 3R cabinet. All the same components, and it's just housed in a cabinet for outdoor installation, and it has a thermostatically controlled heater for the cabinet to maintain the temperature inside the cabinet. So please reach out to E1, contact us, and we can help you out with that.
Okay, very good. Now here's 2 questions on the thermocell. So is the old model of the thermoconductivity cell becoming obsolete, and how long is the life of the thermocell?
So from an obsolescence standpoint, our current purity cell replaces all purity cells that we've ever manufactured. So we've all the way back to the very first one. The part number may be different, but its form, fit, function identical. The second question is the life. We would expect the life of the purity cell to be between 5 and 10 years as a normal expected life. We've got some machines that have been operating 10, 15 years with the same cells, working just fine.
Okay, and here's a bit of a question saying, hello Gus, thank you for your presentation. According to your presentation, are the purity readings of ends approximately 94 to 96% and of case approximately 98%, right? Not 99.9%?
That's correct.
Okay, so the follow-up question would be, why not 99.9% in spite of being used calibrations? Gases are at 99.9%.
Yeah, that's correct. And that comes into play with the design of the scavenging seal oil design, and the tightness of the seals on these generators result in more air being diffused through the oil into the hydrogen, and you get a certain purity as a result of that. So when you go through the GEK, the GE manual for their generators, those values I presented earlier are right off of their literature. 99.9 is very suspicious to me for any generator, because that's more indicative of no leakage, which doesn't exist, or potentially a purity analyzer that needs to be recalibrated, which is more likely the case.
There's a good tip there. Can the DHCP be connected remotely by Bluetooth in order to get its actual measured values or calibration results?
We have been unable to find a Bluetooth that will operate that's EX certified or can operate with the EMI interference of the generator. So those are two design challenges when it comes to Bluetooth. We do offer RS-232 and Modbus communication as an add-on feature, but again, that's over wires. We don't have any wireless transmission available today.
And can I read the hydrogen purity in the control room?
Yes, you can. So there's analog outputs for both purity analyzers that can be brought into the control room with a 4 to 20 milliamp signal. And again, it depends on how much cabling has already been brought down to the unit. You might have to bring extra cabling in to get that signal brought back to the control room.
Okay. Is the thermo cell directly replaceable? Any parameter changes required when we replace the new thermoconductivity cell?
Yeah, that is contingent upon the software version you're running on your machine. So when you call in for your replacement cell, we may ask you to go in and get the software version of your machine to ensure compatibility first, that we have two styles of cells, and also to that exact question, if you need to type in that purity compensation value, which is available only on the newer software versions. And when I say newer, 10 years. So in this industry, new is 10 years old. So,
so clients frequently perform a calibration with just one gas, which is H2. How does this affect the measurement?
That's a great question. I'm going to assume one of my colleagues threw it at me because I forgot to mention that. Yes, calibration must be done with all three gases. And that's because the design of the cells looking at all three gases, and we need to make sure that any drifting that's associated is captured for each of the phases, so each of the gases. So thank you for bringing that question to the forward.
JL asked that question. So thanks, JL. Let's see. Can the DHCP be used on generators with vacuum type seal oil systems?
So that's not the design of the DHCP, because of all of the additional features on the DHCP are associated with scavenging style generator. If you have a vacuum seal oil system, E1 offers many other options for purity monitoring that are more that are focused on the vacuum seal oil design. So if your goal is to upgrade your purity analyzer system on your vacuum seal oil system, please reach out to your local agent or call into the tech support hotline. We can work up a solution for your specific situation.
And I think this is maybe someone who came in late to the game, but what determines when the DHCP will increase the scavenging rate to increase the hydrogen purity?
Yeah, it's a good question and worth repeating. So the analyzer has warning settings, and the control room typically mimics that warning setting for a low purity warning, and that warning is what it initiates the increased scavenging mode. Now that can be programmed differently in the control room, but typically it matches. So if our low purity alarm or warning is at 95, the increased scavenging mode would kick in at 95%. But again, that can vary from plant to plant. The gentleman earlier who was asking about hydrogen consumption, sometimes plants that are running at a 95% point when they go into increased scavenging mode are finding that they're consuming just too much hydrogen gas. So if they adjust that point in the control room to 94 or 93%, obviously with the consultation with their GETA, they'll find that they reduce their hydrogen consumption while maintaining still safe purity levels on the ends based on the age and condition of the seals on that generator.
Okay, well, Gus, you have answered all of the questions that come in. So I think it looks like, as a matter of fact, we're just about out of time. So on behalf of all of us here at E1, we thank you for joining today's session and look forward to seeing you soon. There'll be another webinar series coming out. The next one will be in August. You'll receive information on that. And that will be taking a look at our generator condition monitors, the explosion-proof design. And on that note, everyone be well, and thanks again for attending.